Hello again, and this time we have something completely different. No electronics today, but also something pretty nice, I think. 3 sets of rather unusual dice. The first one here is Platonic solids, 5 different dice. Some of them you might know, some you probably don't know. Then the Go First dice and the non-transitive crime dice. These 2 dice we will discuss in a later episode or 2 later episodes probably, but the Platonic solids we will take a look at right now. All those dice can be used for different things. These here I would say are more educational. You can use them for role-playing games, tabletop role-playing games, or for other games probably. For example, this one here is just a standard 6-sided die, and this is the probably pretty famous D20, which you can use for role-playing, as well as these other 3 solids. So, what do we have here? This here is a 4-sided dice. It's a so-called tetraeder. When you roll it, it will land on one face, and here, not sure if you can see it, let's zoom in. You will see that the numbers of the face are written at the bottom that was chosen, and in this case I rolled a 1. And yeah, you can roll anything from 1 to 4, obviously. It's pretty regular, and that's the whole idea of the Platonic solids, that you have regular polyeder. So basically all the faces on these dice are symmetric. We have triangles here, square, another triangle, also triangle, and even a pentagon. So we have the tetraeder, the hexaeder or cube, the octaeder, which has 8 sides, then the dodecaeder, which has 12 sides, and we have the icosahedra, which has 20 sides. These are our 5 different Platonic solids. And I was wondering, you probably don't know that these are actually the only 5 regular polyeder that exist in 3 dimensions. So basically these are the only regular dice that we can make without having irregularly shaped faces or somehow slanted or non-symmetric bodies for the dice. So there are of course different dice with almost arbitrary numbers of faces, but they will not be as regular as these dice. And it is not quite obvious why this is actually the case. So I thought we might take a look at that and do an actual mathematic proof of why this is the case. So this will probably sound a bit boring, but I think it is not very hard mathematics. Basically you only need fractions, and you all know how to do fractions, I guess, and I will try to explain every step on the way. So let's start. And first, as an introduction, I want to note that these dice have all one property. They are so-called manifold surfaces. And what does manifold surface mean? That means that if you take any surface and cut out a piece, it locally looks like a disk, or basically flat. And an example for a non-manifold surface would be some arbitrary shape with another wall thing or something attached to it, so that you have basically here a piece of wall, then another piece of disk, or thing and on the other side as well. So basically some kind of T-junction. So dice and almost all objects that you construct in real life will be manifold, but mathematically and in the computer you can also describe non-manifold surfaces. But we want to have really existing objects, so our dice that we want to construct will have to be manifold. And there is one nice property of manifold surfaces, that if you tessellate those surfaces with triangles, for example, or squares or pentagons, you can you actually have a nice formula which says something about this. So basically, a tessellation means you take the surface and approximate it by using vertices. Basically, these are the corners of the dice, and you can approximate every shape by using, for example, triangles or squares or pentagons, and you connect those vertices with edges, which are the edges of the dice, which gives you a nice mesh, for example a triangle mesh or a cube mesh or a square mesh, or quad mesh. And those faces will define, those edges will define faces, which are the faces of the die. And now we have a formula which was discovered by Euler, a famous mathematician from, I think, 18th century, but I would have to look it up. And this formula says that the number of vertices minus the number of edges plus the number of faces of such a manifold surface approximated by such vertices, faces and edges always equals 2. That's, I think, pretty amazing by itself, because it's a very simple formula and it holds for every object that you can create, dice or whatever. So let's write this down again. V is the number of vertices, which we marked here in red on the right side, and E is the number of edges. Those we marked black, and F is the number of faces, which we marked blue. Okay, this is the formula that we have to keep in mind. Very important, very useful in showing that there's actually no more than these 5 dice possible. And let's write down what this actually means for our 5 dice. Let's sort via the number of sides that we have. So tetrahedron, hexahedron, octahedron, dodecahedron and icosahedron. So we can write down how many vertices, edges and faces they have. The tetrahedron has 4 vertices, 6 edges and 4 faces. The cube or hexahedron has 8 vertices, 12 edges and 6 faces. The octahedron has 6 vertices, 12 edges and 8 faces. The dodecahedron has 20 vertices, 30 edges and 20 faces. The icosahedron has 12 vertices, again 30 edges and 20 faces. But that's not all that we can write down. We also can write down 2 more things that we call P and Q. P is the so-called face degree, which is the number of edges that are around each face, and Q is the vertex degree, which is the number of edges that are adjacent to each vertex. So at the tetrahedra, both are 3. We have triangles as our faces, and every vertex has 3 edges coming in. On the cube, we have squares, so p is 4, and also 3 edges per vertex. On the octahedra, we have 3 edges around each face, triangles, and we have 4 faces, or 4 edges as well, per vertex. On the dodecahedron, we have pentagons, so face degree is 5, and on every vertex you get 3 edges, which also means 3 faces. On the icosahedron, we get triangles again, and we have 5 edges and faces on every vertex. Okay, so these numbers are actually pretty important later on. And these are basically all the building blocks that we need to see how many Platonic solids there actually are. Okay, what's the next step? Well, there is now some things that we can say about the 5 different Platonic solids. And we can take a quick look at what the cases are that we have here on our hands. So we have the face degree cases 3, 4 and 5 that we have encountered so far. So the 3 is obviously all the cases with triangles, the 4 is the square, and the 5 is the pentagon. Let's complete this so that we have actual faces. And obviously the tetrahedra, octahedra and icosahedra are those cases with different vertex degrees. The cube is on its own and the dodecaeder is on its own. What about cases p equals 1 and p equals 2? Well, they don't make much sense actually. P equals 1 would mean that we have a vertex with 1 edge, and this can be either something like this or maybe looping back. No, probably not, just going out to somewhere else, and we don't get any face at all. So this is not a valid configuration. We can ignore this. P equals 2 means that we have something like this maybe, with 2 edges going out of each vertex, and this doesn't actually make any surface at all, because we can't just arbitrarily draw the edges, so this is also nothing that we can actually do. But maybe cases p equals 6, p equals 7 and so on. What about that? P equals 6 would give us hexagons for the faces, and actually there's no completely obvious reason why this should not work. Similar to p equals 7 and so on. So maybe there do exist more regular polyeder. But let's see how we can prove or disprove this. Oh, come on. What we can now actually do is we take our Euler formula that we had before, V minus E plus F equals 2. We also observe that the following equation holds. If we take the not the vertex degree, not the face degree, but the vertex degree, we can say that every vertex has q surrounding edges and also q surrounding faces. So q times v holds for everything. This is definitely true for every of those regular polyeder. So each vertex has q surrounding edges slash faces. So basically this gives us the total number of faces of the solid. And as well we can say, and we see that every edge that we have on any die, every edge has actually two adjacent faces. So this also gives us the number of all faces of the solid. So each edge has two adjacent faces. Furthermore, we can also observe that each face has p vertices. Each face has p vertices. So what this actually means is any of those terms actually describes the whole solid more or less, and we expect them to be equal. You can also check this in your table. For example, on the tetrahedron, q times v equals 12, which is 2e, which is 2 times 6. So it's correct, and you can go through all the values, and this actually checks out. So what we would expect is that any of those two should equal each other. So basically we can write down that, for example, pf equals 2e, and at the same time qv must also equal 2e, which is a good start. So we basically rewrite this. We divide here by p in the top, so f equals 2e over p, and also on the bottom we get v equals 2e over q. And we can now use this and put this into our equation from above. So let's write again, v minus e plus f equals 2, and we substitute, and so we get 2e over q minus e plus 2e over p equals 2. So that's something we can work with. We can, with the next paper, we can transform this again and divide everything by 2e. Then we get 1 over q plus 1 over p minus half equals 2 over 2e. So nothing magically here. Make this a bit smaller. Basically really just divided by 2e, which gives you exactly this. And of course the 2 you can strike out. And from this follows, because e actually has to be greater than 0, we can actually say that 1 over q plus 1 over p has to be greater than 1/2. I just put the 1/2 on the other side, and we know that e has to be greater than 0. This has to hold. Then, okay, we can transform this further. Let's just put the p onto the other side, so we get 1 over q is greater than 1/2 minus 1 over p. And this is the same as saying q is smaller than 1 over 1/2 minus 1 over p, which again can be transformed to read q is less than 1 over p over 2 p minus 2, and this is the same as q is less than 2p over p minus 2. And this is already a pretty important result. Let's note this down, because this we can test out. We can just put in different values. And what combinations of this can we choose? I'll put this to the side. So basically what we already said is that our vertex degree has to be greater or equal than 3. Our face degree, sorry, has to be greater or equal than 3. And at the same time we also know that our q definitely has to be greater than 0, but we can even say it has to be greater or equal than 3, because for the vertex degree it also doesn't make sense to be smaller than 3. And our last result says this has to be smaller, definitely smaller than 2p over p minus 2. And now we can just run the numbers, because there's not so many cases actually. First of all, start off with p equals 3. Then it follows that 3 is less or equal than q is less than 6 over 3 minus 2, which equals 6. Okay, so what possible combinations can we have? PQ can be either 3 and 3, for example. 3 is less or equal than 3 and equal less. This is a bit stupid. Yeah, let's write this. Oh, that's actually, that was actually okay. Ignore that. So, and this is less than 3, the less than 6 definitely. Second would be 3 and 4, also possible, and 3 and 5. So let's bring in our sheet again from before. 3, 3, yes, we have that. That's our tetrahedron. 3, 4, yes, we also have that. That's our octahedron. And 3, 5, we also have that. That's our icosahedron. So these 3 we have. We know that those exist and they are fine, and no surprises here, no new solids. Next, p equals 4. So this is basically all the squares. Here it follows that 3 still has to be smaller or equal than 3, and it has to be smaller than 8 over 4 minus 2, which is basically 4. So what possible solutions do we get here? Well, 4 and 3. That's it. Because the only number which is between 3 and 4 excluding is obviously 3. Let's bring in the sheet. We have 4, 3, and yes, check. That's our cube. And nothing else there that is actually possible. And third case. Third case would be p equals 5. So we have 3 is less or equal than q is less than 10 over 5 minus 2, which is 10/3, which is something 3 point dot dot dot. I don't care. So basically it has to be smaller than 3 plus epsilon. So all possible solutions are 5 and 3, and that's it again. Nothing more possible, otherwise we will be bigger than 3 point something. Do we have this? 5, 3. Yes, of course we have this. This is the icosahedron. And actually, the dodecahedron. Actually, there's a mistake here. Number of faces is, of course, 12. But you probably already noticed that before. Okay. Question is there anything possible larger than 5? For example, 6. So 3 is less or equal than q is less than 12 over 6 minus 2, which is 12 over 4, which is exactly 3. So we're looking for something 3 less or equal q less than 3. This is obviously not possible. And it's obvious now that the higher you get with a p, the smaller this number will get. And everything above 6 will not be possible. Which means that there can't ever be any more regular polyhedra except for these 5 little things. And those are the only regular dice that you get. And I think this is quite a nice proof because it is relatively simple. You don't need any high mathematics, you need to know what inequalities are and some small fractions. But that's basically it. It's a bit of combinatorial thinking and yeah, pretty amazing result I think. And next time we'll take a look at the other weird dice that I've got. And so far I thank you for watching. I hope you learned something and had some fun. And you can share, like and subscribe to this video. And as always, thanks for watching.